So thank you, Esperanza. This is the presentation for the status update of the project DeepR. We are going to talk about what the project is about, our methodology, also the implementation in a Python package, and the main results that we have obtained till now. First of all, we want to talk about the members of the team. We are all of us from Spain, from Santander. We work in Predictia, and a spin-off from the university here in the community. And Javier works for the Institute of Physics of Cantabria, which is also related to the university. The challenge is mainly proposed to downscale the coarse spatial resolution data from ERA5 to a higher spatial resolution like the one that CERRA proposed. We are going to do this through the use of machine learning techniques. And for those who don't know what is Reanalysis, Reanalysis is a comprehensive reconstruction of historical weather, assimilating data such as real observations, satellite data, and so on, combined into a numerical model. These reanalyses are really important because they provide consistent information of historical weather conditions, and they serve as a very important resource to those who have to make the decisions in our society. Also, it is important for assessment of climate projections or numerical weather predictions. But there are, for those who are familiar with the reanalysis data, the ERA5 global reanalysis is one of the most commonly used reanalysis data sets, and its resolution is around 31 kilometers. So in many sectors, they need a higher resolution to capture the finer scale details, which are critical for localizing weather patterns, and also they enable to understand the more complex atmospheric processes that are inside the models. So the project motivation is to go from a coarser spatial resolution from around 0.25 degrees, like the ERA5 one, to a higher resolution, like the CERRA one, with 0.05 degrees. This issue is illustrated in that image where we can see that ERA5 do not depict pretty well the Pyrenean area here in the Iberian Peninsula. As a first step for the project, we have defined a smaller domain in order to reduce the data complexity during the development stage. We have taken an area where we consider mountains like the Pyrenean area, also a land-sea transition like the one in the Mediterranean Sea. Also major cities like Madrid, Barcelona, Valencia, and large lakes that are located all over the north of Spain and also in the Mediterranean area, and several islands corresponding to the Balearic Islands. And just to wrap what I said before, the main purpose of the project is to design a deep learning algorithm with models and architectures that Mario is going to explain later, to generate estimates with the same resolution as CERRA.
Hi everyone. So I will talk now about the methodology we are implementing. We have proposed an AI-based solution for generating these high-resolution grids. In particular, during this challenge, we are researching about the use of diffusion models because they are now the state-of-the-art in image generation tools like DALI or Midjourney that all of you may know. They have like the main advantage they have are like its learning capacity, the extrapolation to new data, and also the realism of the predictions. Now I will briefly explain how these models work. During training, you just try to add noise to the target images until you get random noise. And during that process, you are training a neural network to learn the added noise at each time step. So during inference, you can apply iteratively this neural network to the noise, random noise, into a final grid, high resolution grid. But these techniques has also important drawbacks that are mentioned below, and we have tried to face. For example, the training efficiency and the scalability of this model. To face this, we first reduce the domain area, and we are also considering the implementation of latent diffusion model to what we have implemented a vector quantized variational autoencoder to work on the latent space of the grids instead of the full grids. We have they also have long inference times. To this, we have implemented state-of-the-art noise cellulars to reduce these sampling steps during inference. As this technology is very new, a lot of architectures and schemes are being published. So it's important also to tune the networks. And finally, another point of interest is how you add additional constraints or covariables to this dataset, as it can be the hour of the day or the day of the year. So here, some of the plots we consider during validation. Some of them are very general, like the error matrix or R squared, but there are also more specific validation, limiting to specific dates or areas of interest that can tell us how these meteorological predictions work in comparison with CERRA. We have implemented a Python package under the common repo that is tracked there, DeepR, and we have considered a pipeline that does all the process from dataset preparation, the model architecture loading, and also it trains and saves the model. It is prepared to be trained with CUDA, so it's very efficient. It also implements the validation. This pipeline can be run all in once or only the validation if you want to validate a trained model. We use files to configure the pipeline, like the ones you see here. And now we are presenting some of the results we get. Just briefly for the diffusion model, the first one we trained, you can see the samples comparing the prediction with the target. the target is the second row and the prediction is the third one. The border, you can see that the model is clearly learning something, but it doesn't get the high resolution structures from CERRA. Here we also include another metrics like the loss function over training or additional metrics. And we also train a regular neural network for downscaling the ERA5 directly to CERRA. And we can see that the difference with the cubic interpolation is very small. The general improvement is around 5%. So there is not much improvement over this with this type of networks. You can see that this network has a lot of improvement over the coast, but yeah. Here some additional error plots of the baseline method against the neural network for a given sample. As the next step, we are training now a diffusion process, but guided with the upscaled ERA5 image instead of coarse ERA5 grid. And then we want to train the latent diffusion model and other options like the percentage there. So at the end of the project, all models will be openly available through Hugging Face. You now can check the repos to see the model checkpoints and also the training metrics and validation plots. So thank you very much.
Thank you very much, Antonio, Mario, for your results. We are looking forward to the second part of the coding phase when you finish your exploration. Yeah. We have a question from Florian Pinault. Which metric did you use for the training? Do you expect the choice of the metric to have a strong influence on the results?
For the diffusion model, we use L1 loss. We don't expect much difference comparing to L2. In the normal neural network for super resolution, we use L1 loss with additional terms to evaluate the spatial consistency that are typical in these super resolution tasks.
Thank you. We have another question from Noelia Otero. Did you use any pre-trained model? And as an input, did you include orography?
No, we didn't use any pre-trained model. We have implemented the option to pre-train these models. And the idea of training a regular neural network was to use it as an input for the diffusion process, to guide the diffusion process with an estimation of the high resolution grid. We don't include orography now in the models because we are considered static images, but we are, for example, including it in the validation step to see the difference between different orography levels.
Thanks. We have the last question from Kiko Correoso. Do you need just one variable for the downscaling, or are you considering more than one in different levels?
For during this challenge, we are just considering one variable. If we would have time, we would like to try considering more variables or also more time steps of the same variable. But now we are just considering one variable.
Thank you. Thank you very much, both of you.
Thank you.